Hi everyone, I am Pedro, and today I'll be presenting Solidifier, which is a bounded model checker for the smart contract language Solidity. And this is joint work with Bill Roscoe. Let me start by giving you a brief overview of this presentation. I'm going to start talking about blockchains and specifically about Ethereum and smart contracts. I'm going to move on to discuss a little bit the motivation for verifying smart contracts. And then I'm going to talk about Solidifier, how we formalized Ethereum and smart contracts. What are the challenges that we faced? What is the structure of our bounded model checker? And I'm going to try to give you some rough numbers of an evaluation that we carried out where we compared Solidifier to similar tools. So a blockchain is a transaction processing system. It basically receives transactions, processes them, and this processing of transactions will lead to some alteration of its underlying state. So the state of a blockchain is split into addresses, and an address can either be unused. It can be a simple address that simply is associated with a balance, or it can be an address that has a smart contract deployed. And in such address, not only it has a balance, but it has some data that captures the state of the smart contract, and it also has some code that basically manipulates and manages the digital assets that are controlled by this smart contract. So, and we're going to represent this, the state of this blockchain by such a collection of addresses. A blockchain like Ethereum also has some transactions that you can issue. As I mentioned before, the most basic one is a coin transfer transaction where you can just move some coins from one address to another one. But here we'll be mostly interested at transactions that interact with smart contracts. And here we are showing two transactions. One is contract deployment, where you can create a new contract in the blockchain, and another is contract execution, where we can actually run some smart contract code. Before I move into discussing these transactions and what they do, let me try and introduce what smart contracts are by giving you this small snippet of a smart contract written in Solidity. Solidity is perhaps the most widely used language to write smart contracts. And in this case here, we're simply presenting this very basic wallet contract where other addresses can basically deposit some of their coins inside this wallet. So in Solidity, you can have that a smart contract can define some types. Here we have an enumeration status to define the status of an account. An account is then defined as the struct that has a number of coins that is basically the number of coins that this account holds and the status of the account. A contract also has state variables, and these state variables will actually represent the state of the contract. Here we just have this mapping, and this mapping is basically just a hash map from addresses to accounts, and this will tell us which address owns however many coins is in this account. And in a smart contract, you also have some functions, and these functions can be triggered by transactions as I showed before. So here we basically have this wallet where, as I said, smart contracts can deposit and withdraw coins to and from it. All right, let's move back to the transactions relating to smart contracts. One of the things that you can do is basically deploy a new smart contract. Here, for instance, we could have that address to was unused, and then we issued this contract deployment transaction, and now address to has a wallet smart contract. And you can see here that the balance is 0 because we just deployed the smart contract, and the account mapping is empty because no accounts have been created. Let me just move on and discuss now contract execution. So here we could have that address 1 is actually trying to open an account with address 2. And as you can see here, this transaction would trigger the creation of this new mapping here that basically describes that address 1 now has an account in the wallet. And just to bring this home, we could have also a transaction that would deposit some money from address 1 inside address 2. And you can see here that we're depositing 5 coins. So address 1 now has a balance of only 5. Address 2 has a balance of 5 because 5 coins were deposited in. And now this mapping has been updated to reflect the fact that address 1 has deposited 5 coins inside the wallet. All right, and what is the motivation for the verification of smart contracts? First of all, in Ethereum, smart contracts are immutable. So once you deploy them, you cannot patch the code of your smart contract. So if there is a bug, it's not an easy thing to fix it. They also manage digital assets, and these digital assets are worth a lot of real money. So hackers have quite a big incentive to actually go and try and misuse your contract. And Solidity is also a quite immature language. And the smart contracts are also something very new, at least in practical terms. So we don't have enough maturity to write good and well-defined and well-behaved smart contracts yet. And just to give you a brief example of an attack on a smart contract, this is a very small toy version of the wallet contract I just showed, and it seems like a very innocuous contract, but it has in fact quite a damaging bug that would allow someone to deposit basically 1 coin and take out as many as they wanted. This is, as you can probably guess, a pretty devastating bug that would basically cause all the digital assets that are managed by this contract to be completely compromised. And this smart contract only has like 10 lines of code. So you can see how easy it is to just add some bugs here and there that will completely defeat the purpose of smart contracts. And just to show that this is not only an academic problem, we do have quite a few examples of different attacks on smart contracts where quite large sums of money have been compromised. So, all right, moving into our formalization now. In Solidifier, we used Boogie to formalize Ethereum and Solidity smart contracts. Boogie is a simple but powerful imperative language. A program in Boogie, like with many imperative languages, has global variables, procedures, but it also have this special specification statements. So you have assume, assert, and havoc statements. With assume and assert, you can actually include some mathematical statements within your program and in some different program points that can constrain the state of the program, which is something very useful. And havoc can basically non-deterministically initialize variables. So those things are quite useful tools when you are formalizing or specifying the behavior of a programming language, such as Solidity. All right, as I said before, we formalize Ethereum and Solidity as a Boogie program, and the global variables, they will basically account for the state of the blockchain and its execution. And the 2 main variables that we have in our formalization are the state, which captures the persistent state of the blockchain, and this memory variable. And this memory variable just captures this volatile block of memory addresses that Solidity uses to process transactions. And what we have is that procedures in our Boogie program will actually be used to capture Solidity functions. So here we have just a glimpse of all the procedures that are created, for instance, for this wallet contract snippet that I just showed. Just to give you a little bit more insight on how we capture the state of the blockchain, we have basically this mapping from addresses to address cell, and this address cell is just a struct, a record that will capture the state of the corresponding address. And what we have here is basically a type, which can either be unused simple or the name of a specific smart contract, if this is a smart contract instance. We have the balance of the smart contract, and we have these 2 last elements in this record, members and storage, which will store basically the state of the smart contract deployed at this address, if this is a smart contract instance. All right, let me talk a little bit about the challenges that we faced in formalizing Ethereum and Solidity. So Solidity has a very unorthodox memory model that we're going to talk a little bit more about. So it has this deterministic allocation model, and also the semantics of assignment varies according to where variables are allocated. And there is also this slightly unconventional thing, if you compare to traditional programming languages, that contracts can be deployed on the fly. So let me briefly elaborate on these challenges and talk a little bit on how we try to solve them. In Solidity, we have deterministic allocation. So whenever you deploy a contract, you already know at that point where each element of its state, where exactly they will be placed in storage. And this does not change as the contract evolves. So for instance, in a traditional programming language, you would have that if a vector grows too big and cannot fit in contiguous memory space, it will be moved around and placed at some other part of the memory where you do have that many contiguous memory spaces. In Solidity, that does not happen. Things are allocated when the contract is deployed, and they are to for the entire life of the contract, they are at the same exact place. How we formalize this using Boogie, we created this allocate many code block, and what it does is eager and unbounded allocation of dynamic types. So mappings and dynamic arrays are completely allocated at the creation of the contract. And this is possible because we do have the ability of creating these quantified formulas that basically says, I would like any memory address that is mapped by this either array or this mapping to be allocated at one specific point. So this is quite a nice feature that we can implement using, or that we can specify using Boolean. In Solidity, you basically have two distinct memory spaces. One is called the memory, and it is volatile, as I explained before, and the other is called storage, and it stores the persistent state of a smart contract. And depending on where the variables are, you can have different semantics for the assignment operation. In the paper, and I put it here, we have this nice table that tells exactly what the semantics is according to different possibilities of variables on the left-hand side and right-hand side. In Solidity, smart contracts can be dynamically deployed, and one of the things that you could have is that you try to call a function at an address where a smart contract has not been deployed yet. And to avoid such things that wouldn't lead to anything interesting in our analysis, we require that whenever we call an address that is unused and we are expecting a smart contract to be there, we will deploy that smart contract there in a non-deterministic state. And we call this thing lazy contract deployment. So instead of having a contract call that would fail and would amount to no useful exploration, we do this lazy contract deployment, and we can actually have a proper call of a smart contract instead. Another and the last missing piece in our exposition of Solidifier are verification harnesses. Once we formalize and specify the behavior of Ethereum and a Solidity program, we need a verification harness to basically drive the behavior that we want to analyze. We propose two different harnesses in our paper. One is a contract harness, where we try to analyze as closely and as faithfully as possible a specific smart contract. And the other one is a function harness, where we basically try to analyze a specific function of a smart contract. And while in the contract harness, we try to properly deploy and execute methods of a smart contract in the function harness, we non-deterministically initialize the contract that we are trying to analyze. So while the contract harness is more precise, the function harness can actually find errors that are deeper in the execution of the smart contract, which can be something quite useful as well. So what does Solidifier look like? So given a Solidity program and a verification harness, it will have this encoder that will generate this boogie program as we just described. And this boogie program will be fed into Coral. Coral is a CIGAR-based bounded model checker for boogie. And what will come out of our bounded model checker is either that the program has been verified, that it has been verified up to a specific bound, or some assertion in the program has failed, or some unknown result. We do use in our specification some theories which cause our problem to be undecidable in the general case, so we might get unknown results. And just some nice usability features of our bounded model checker is that we lift the output given by Coral, that is obviously for the boogie program, back into the Solidity program. So you can have nice messages that reflect what the state of your actual Solidity program is. We do try to present a trace for failing assertions. And not only this, but we do have specific functions that allow you to print values at different program points. So this can be quite useful when you're trying to debug some Solidity program. We conducted an evaluation where we tested Solidifier against SOC Verify, Verisol, and Withrow. The first two are also boogie-based tools. And out of 31 examples, you can see in this table that we overperformed these other tools, and we did quite well. And in the paper, we go into more details on what these examples are and what the results actually are. I just want to make sure that it comes across that Solidifier, based on this new encoding that we propose, we do get quite a nice improvement on similar tools. Okay, to conclude, we present here a bounded model checker for Solidity, and it accurately captures Solidity's memory model. And we also use lazy contract deployment to go with dynamic creation of smart contracts. And just as a final thought, I work for a very nice startup based in Oxford, UK. And we innovate around trusted technologies, and specifically blockchain and trusted execution environments. And we do have a research partnership with University College Oxford, and we are always looking for talented people. So if you're interested, please do reach out to us, and we're really glad to start a conversation about how you fit it into our picture. Thanks a lot.